Thank you. Pleasure to be here. And I'll be talking about energy-weighted site percolation in 2 dimensions. I will explain what that means. This work is done with the graduate student at TIFR Hyderabad. Percolation in 2 dimensions has already been introduced to you. It's a cornerstone of statistical mechanics. Sites of bonds and lattice are occupied with an independent probability P. There's a well-defined critical probability below which the system consists of only isolated clusters. Above PC, an infinite spanning cluster emerges that connects opposite sides of the system. This represents a second order purely geometric phase transition. Critical exponents such as the correlation length exponent or beta, which is the probability of being in an infinite cluster, depend only on the dimensionality of the system, not on the underlying lattice. So d equal to 2, which is what I will discuss today. For example, the correlation length exponent is known to be exactly 4/3 for all 2D lattices. And so the question we are asking today is, can we come up with some percolation models where this number can be changed and we can create different structures using very similar definitions as what is done in classical percolation. So in order to do that, I would like to connect it to something that is another field of study that is of interest to many people in statistical mechanics, that is hard-core lattice gases. So here's a configuration of a hard-core lattice gas with only pure on-site exclusion, which means that particles can occupy single sites and no two particles cannot be at the same site. So the occupation number of each site is either 0 or 1, and the particles are represented as green circles here. With each particle, you associate a fugacity, typically which is the exponential of a chemical potential, and then you can just write down the grand canonical partition function. For this very simple on-site exclusion lattice gas, you write down the grand canonical partition function as the summation over all possible configurations with the fugacity to the power of the number of particles in that particular configuration. So we can just start to write it down, which is basically Z0 is 1, which is a completely empty lattice. Then you can add 1 particle, which has the weight factor Z, and that can be in any of n choose 1 places where n is the total number of sites in the system. And similarly for 2 particles, then choose 2, and without much work, you can easily figure out that this is just a binomial series. And so the partition function for such a model is just 1 plus z to the power n, no singularities, analytic function. But how is this connected to site percolation? Well, you can just take this partition function and calculate the density, which is just a derivative with respect to the fugacity of the free energy. And once you do that for this very simple model, you'll just get the density z by 1 plus z, which is a very simple smooth function, interpolates from 0 to 1 very nicely. But then one can notice that if one were to connect z and write it down as something as a variable as p into 1 minus p, sorry, p divided by 1 minus p, what you get is that the rho naught, which is the density that you have predicted, is precisely this number p. So, which is what we were doing in percolation, which is the sites are occupied independently with probability p. So if I was to get a fugacity of this on-site exclusion lattice gas and connect it to the to the probability of occupation, I can just get the exact model of percolation that I was talking about. So starting from this hardcore lattice gas, I can then ask the following question: is there a percolation transition in this lattice gas? One can then simply generalize this percolation question to slightly more interesting lattice gas models, where you just turn on an interaction energy between nearest neighbor bonds. This is not such a trivial thing to do, because as soon as you turn on an interaction energy, this model becomes quite hard to solve. For example, just a nearest neighbor interaction energy becomes Ising model in a finite magnetic field with this simple mapping. Won't go into that in detail. So what do we do now? So we just take this model of interacting energies and particles and just say, okay, why don't we devise a grand canonical partition function in the same way with this mapping that I had given previously, which is z is equal to p by 1 minus p, and the partition function for this model that I've defined, which is the energy weighted site percolation, that is the number of bonds in the clusters that are created in this configuration, which is represented by this number t, will basically weight the configuration in addition to what you would get from just simple site percolation. So this energy enhances or disallows the nearest neighbor occupation for one percolation. And just to complete the story, you can just look at the density versus p for different energy weights. So if the energy weighting was 0, which is over here. It's just a straight line because that's exactly how we define rho should be exactly equal to P. But if you now add positive energies or negative energies, you can change the occupation probabilities of the sites. Well, so you can just define this microscopic model. They have energies Ex in the X direction, Ey in the Y direction. You can have different kinds of energy weights. So what does it look like? So isotropic energy weighted percolation, as you increase P in this direction and you increase E in this direction, you see that you can start to create very different kinds of clusters. With negative energy, the system like the clusters like to sit next to each other, so you get these very compact looking clusters. But if you have positive energy, there's an energy cost of sites being occupied next to each other, so you get this emergent antiferromagnetic order. Similarly, you can create for anisotropic bond energies, you can vary between Ex and Ey, so you can basically create patterns that are more percolating in the Y direction or percolating in the X direction, and this is the isotropic limit. And here Ex is greater than Ey, here Ey is greater than Ex. So you can create a whole host of patterns based on this lattice gas models with which to study percolation transitions. So I won't go into the details of the computation, but what you can show is that by changing P, which is not really not really exactly the site occupation probability anymore because of the mapping to the fugacity, P versus E can be computed, and this is a percolating and non-percolating phase. So when you have low P, when you have high energy and high P, you get a non-percolating phase, whereas in this region you get a percolating phase, and you can actually see that the E equal to 0 is a classical percolation site percolation transition at 0.59. You can then look at the scaling and the critical exponents of this with different energies, and which we have done, and you can see that there's a small variation in these exponents, which we can then try to explain using different renormalization group techniques. What we found useful was this very nice work that was quite well known in the early percolation literature, where you can do real space block renormalization, and you just assign some rules where you say that the block is either considered occupied if the cluster spans either horizontally or vertically, which is some rule R0, R1 where the block is spanning in only one direction, and R2 is that it's occupied if it spans both horizontally and vertically. So using these kind of definitions, you can go into the renormalization group of such a system, and then here are our predictions for the RG, where you can say that the critical percolation probability, this is computed using different block sizes, B equal to 2, 3, 4, and 5. After that, the expansions become quite hard to do, but we can push it to up to about 6. But here itself, you can see that the PC versus E can be predicted very nicely. There's a smooth crossover here, which then we can do simulations and see that they're quite close. So actually, the PC predictions are quite close here. Similarly, for the nu, which is the exponent for the correlation length, we can actually predict using this block RG. Comes out to be quite, I would say, close to the experiments, but not really exactly in line, because this is still an approximate RG. But we can do these exact numerical experiments and check that there is a tunability of these critical exponents with energy. So, and then we can see how the antiferromagnetic order comes in. But just to summarize, we have energy weighted site percolation, which provides a tunable generalization of this percolation, which is very well known. RG methods can tell you that there is a continuous evolution of these exponents, and which we can also somewhat argue from Coulomb gas techniques. I won't go into that. There's antiferromagnetic order at high energies, and we can try to explain that. But we can also, of course, extend it to bond percolation in higher dimensions, if not theoretically, at least numerically. And with that, I'll take some questions.